I wanted to start with some exponential derivatives, just because I think these are things that people probably have forgotten about more. We'll see. So again, I'm just taking derivatives here, but if I've got e to the something, then that derivative is going to look like e to the something times the derivative of whatever that something was. So in this case, the derivative of 7x is 7. Now over here, this is an exponential. I know it's an exponential because that x is in the exponent. And I'm going to pause this for a second. My dog and cat are sort of playing together in the hallway, and it's loud on my end. So I'm going to go shut my door. Sorry about that. So this is an exponential because my variable is up in the exponent. So the derivative for any of our exponentials, really the format is always the same, but I'm going to end up with exactly the same thing I started with. Times the derivative of whatever was up there in the exponent, times the natural log of whatever the base was. So in this case, my base on the exponential was 7. So this would be times the natural log of 7. Now, I said that's always how it works for derivatives of exponentials, because secretly, if I go back to the e to the x piece, I could have inserted here natural log of the base, which is e, and the natural log of e is equal to 1. So we don't usually write it when we've taken the derivative of something with a base of e, but technically that ln of e still kind of could have been sitting in there. Did anybody have questions from any of the other derivative practice problems I posted? And you can either raise your hand, type it in the chat, or give me a yes. Seeing nothing, I'm going to move. Oh, yes. So you have time to do them together. We definitely have time to go through all of them together. So let me just pull that up really quick. And I know that a couple of you had posted in my quiz of like me, let me get to know you a little bit. A couple of you posted that you didn't take 17A in the winter quarter, that it's been longer than that since you did first quarter calculus, which is kind of why I put up the derivative practice, just to get it fresh in everybody's mind before we start doing anti-derivatives. So oh, I've also got this note up here to everyone that if I make a mistake, please speak up. I saw a bunch of you in Didel's office hours today, and I'm guessing that somebody else caught his mistake before he did when he was trying to add fractions, and he kept calling 2 over 4. If I am making dumb arithmetic mistakes like that, somebody please speak up. You know you'd call me out on it if we were in class together physically, so don't be afraid to do it online. Okay. And I see a couple other questions coming up in the Zoom group chat, and for sure we will definitely do some of the 5.1 graphing kind of problems. So I'm going to blast through the problems from my derivative worksheet. So we've got y is equal to 3x to the 6 plus 5x to the negative 2. Oops. Minus 17. And I know my board is at kind of an angle, but unfortunately the glare from my window gets really bad if I straighten it up. So please let me know if it's not big enough, and I'll just write bigger. Okay, so this is what I like to call algebra, because it's just numbers times x's raised to powers. So in general, when we're taking these derivatives, I'm taking that exponent, multiplying it by the coefficient in front, and subtracting 1 from the exponent. So I have 3 times 6 x, and then subtracting 1 from the exponent, I'm down to x to the 5th. Same rule works even if it's negative exponents or fractions. We just have to be careful about the subtraction piece. So I'm going to have 5 times negative 2. And when I subtract 1 from negative 2, I'm going to end up with negative 3. Now the derivative of negative 17 at any other constant is 0. If I look to this second one here, I've got y is equal to 3 over x squared plus the square root of x. And if I were doing this problem in 17a, the first thing that I would do is to take that and to rewrite it so that it looks like number times x raised to a power. So I would look at that and say that's like y equals x to the 3x to the negative 2 plus x to the 1/2 power. Then I'm ready to take the derivative. So now my dy dx, same rule, bring the power down, subtract 1 from the exponent. Bring the power down and subtract 1 from the exponent. So 1/2 minus 1 is going to give me a negative 1/2. And I'm kind of watching for raised hands. You can click that raise hand button in the Zoom chat if you do want to slow me down or ask a question about something I've just written. Okay, third problem. This one's going to be really quick. Y equals cos, oh, I wrote the wrong problem. We'll just squeeze this in here. Y equals cosine of 3x squared. So if you have forgotten those trig derivatives, it is, and I will address the question that just popped up in a second. So if you have forgotten those trig derivatives, it is time to review them. But our derivative of cosine is negative sine. And on this one, we're going to peel off those layers. So I have cosine of another function. So cosine is kind of the outermost layer. So when I'm thinking about chain rule, I'm taking that derivative of cosine first. And the derivative of cosine is negative sine. And I made a big deal about this in 17a. But when you are taking the derivative of a trig function, we never change the argument. Only a trig identity can actually change what's inside of the trig function. So we took this derivative of cosine of something, and that something is acting like our angle. So we can't change the angle. It's still 3x squared. And then chain rule says, now we're going to multiply by the derivative of that inside part, or 6x. So I'm going to rewind back to number 2. And there was a question about, could I have written the answer in a different way? For sure. So this was y equals 3 over x squared plus the square root of x. And based on the answer we got, we could have also written this as negative 3 over x cubed plus 1 over 2 root x. In terms of would you get full credit either way? Absolutely. So Dr. Diddell can be a little bit picky on how you simplify a problem. However, this is a case where he definitely won't care whether you write it like, oh, sorry, this would have been a 6 from the previous problem. This would give you full credit, and so would the -6x to the -3, and the 1/2 x to the -1/2. Either of these would be totally fine because they're both considered a simplified form. If you were looking for the answer in the back of the textbook, it's going to match this one, not the bottom one. But either one is totally fine. And hopefully that answered the question about being able to write it in a different way. Okay, just 2 more quick problems from the worksheet, and then we can move into section 5.1. Okay, problem 4. Got y equals natural log of 4x plus 1. And when we're taking derivatives of natural logs, I'm going to end up with 1 over the something times the derivative of the stuff. So y prime is 1 over 4x plus 1 times 4, because it's the derivative of the inside. And 5, I threw this one on there just because, depending on who you took first quarter calculus with, and especially if any of you are coming from Math 16A instead of Math 17A, you might not have seen the derivative of inverse tangent. This one is going to show up a lot for us in 17B, especially in Dr. Diddell's class. So it is important that you're comfortable working with the derivatives of the inverse trig functions, because we're going to be expected to find antiderivatives of what comes out. So in general, for arctan, that derivative is 1 over 1 plus whatever the angle was squared. And then we'll just have to remember to do the chain rule in this case and multiply by the derivative of the inside, which is 5. And we are being asked to estimate the area from x equals 0 to 4. And it looks like we are using 4 rectangles, and we're going to do this with both left endpoints and right endpoints are the 2 parts in terms of A and B. So this gets back to most of what Dr. Diddell was talking about this morning. And I'm just going to take one quick step back. So if we think about trying to approximate that area, stuff that we know how to find area of, like from pre-calc, well, we can find areas of circles, or at least you ought to be able to. We can find areas of triangles. We can find areas of trapezoids. We can find areas of rectangles. But we probably don't have a formula to find the area of a square root of x. So what mathematicians did a long time ago is to say, well, we can approximate that area using a shape that we do know how to find the area of. And at least for right now, the shape we're going to use is a rectangle. So the idea is that we're going to walk into this shape and imagine breaking it. Oh, you know what? Someone is saying the question is in 5.2. Did I grab the wrong problem? Oh, no. They're asking about the question from 5.2. No worries. I'm going to do this one, and then we'll jump into 5.2, number 4, since I've already gotten started on this one. So I'm trying to write this, trying to find this area, breaking it into 4 pieces. Because the numbers are nice on this, if I break this into 4 pieces, then each of those x values is going to land on a nice whole number for us. Now, there really isn't any trick to doing this with rectangles. When we get into 5.2, things actually get a little more complicated. But in 5.1, you could do this problem entirely just from your geometry skills. You don't need to know any special formulas. You just need to know that the area of a rectangle is the base times the height. Now this problem talks about using right-hand endpoints and left-hand endpoints. And what that means graphically is if we're using right-hand endpoints, then we're thinking about drawing a rectangle in here, 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 and here. But in each of those intervals, we're going to figure out the height of the rectangle by using the x value that's on the right-hand side. So for that first rectangle, I'd be using an x value of 1, which if the x value is 1, then to figure out the height of the rectangle, I'm using the function to get the y value. So if x is 1, then my height is 1. For my next rectangle, I'm again using the right-hand endpoint, but of the next interval. So now my height, my x value is 2, and when I plug it into the function, that height is square root of 2. Same thing here. And for my last rectangle on the right-hand side, that's going to be a height of 2. So when I go to find the area of each of these rectangles, if it's a base times a height, then this last rectangle, it has a base of 1 and a height of 2. This rectangle also has a base of 1, but it has a height of the square root of 3. That second rectangle in there has a base of 1 and a height of the square root of 2, and my first rectangle had a base of 1 and a height also of 1. So to estimate the area under the curve, I would be adding all of those areas up. Notice that because we chose equal widths for those subintervals, and this is something that Dr. Diddell was doing in his problems, they each have the same base. So we can actually kind of factor that out of the formula and have the base and then times adding up each of the heights. So for us, that was going to look like each rectangle had a base of 1, and then when we add up those heights, that was 1 plus square root of 2 plus square root of 3 plus 2. And I think I'm just going to leave it there. I will draw in, oh, by the way, part of the question in the textbook asks, is this an overestimate or an underestimate? For this particular function, this is an overestimate, because if I look at each of those rectangles, they're all a little bit bigger than what the actual area under the graph would be. Now, if I go to left-hand endpoints, and I'll do a different color here, my picture will get a little bit messy, but if I do left-hand endpoints, then on this first interval, the height that I would be using is 0, because that's the height at the left-hand endpoint. For that second rectangle, my x value that I would be using is 1, so that rectangle would get cut off right there. So the area, if we were using left-hand endpoints, I'd have 0 times the width of 1 for the first rectangle. That second rectangle would have a width of 1 and a height of 1. My third rectangle would still have a width of 1, but a height of square root of 2. And my fourth rectangle would have a width of 1, but a height of square root of 3. For this particular problem, that would make the left-hand endpoints an underestimate, because each of those rectangles is less area than the curve. I want to stop and point something out. Sometimes students think, oh, the left-hand endpoint is always going to be the underestimate and the right-hand endpoint will always be the overestimate, but it depends on the shape of our graph. So if I had a graph that looked like this, and I was drawing in my rectangles, let's say I was drawing in 3 rectangles here, and I did left-hand endpoints, then based on this graph, those rectangles would look like this. And in this case, the left-hand endpoints would actually be our overestimate. So it isn't enough to just know that it's left or right, to know that it's an under or overestimate. You really want to be thinking about what the actual graph looks like. Okay, I am going to go to section 5.2 and look at number 4 in 5.2. Okay, this one's a little bit, no, it's a lot messy. I'm not gonna lie. It's a lot messy, but we can do this. So let me bring my Zoom window back up. But let me pause just for a second. I'll check for raised hands or comments in the chat about this problem before I erase it. Lynn, did you want to ask your question?
Sorry. Yes. So if the graph curve is in the negative section, how would the like overestimate, underestimate work?
So if my graph and again, this is not something that's talked about in section 5.1. This is a little bit further in the textbook, but let's say that I have a curve where some of the area is below the axis and some of the area is above the axis. So the issue here is that if we're thinking about the area as the base times the height, then these heights actually have negative values when they're below the axis. So in terms of whether this is an overestimate or an underestimate, that really depends on the exact wording of the question about an underestimate or an overestimate. So if I was talking about the area, as in the area of this shaded region, then my rectangles are still an overestimate of the shaded region because my rectangles live outside of that region, and like the absolute value of the areas of those rectangles would be more than the area of the region. So I don't know if that really answered your question, but I will say it's not a question that I see asked very often if the graph includes both area under the curve and area above the curve. And we've got another question in the chat here about the square root of 2 and square root of 3 for the y values on this graph. Yeah, excellent. So the way that I'm getting the heights, and I'm going to erase a little bit of this so that it's, I've got a little more space, but so in general, with any kind of graph, if I'm trying to figure out the y values, then I'm going to get that from looking at the function itself. So here the function that we were given is the square root of x, which means that if I'm at an x value of 1 and I plug 1 into the function, then I'll be at the square root of 1, which is 1. So at an x value of 1, that y value works out to be 1. But when I'm here at an x value of 2, if I plug 2 into the function, I'm going to get the square root of 2, which means that point on the curve is at the point 2 comma square root of 2, meaning the y value or the height at that point is square root of 2. Similarly, if I'm at an x value of 3 and then I come up to the curve to figure out what that point is, then I'm going to plug 3 into the function, end up with the square root of 3 for that height, and that's going to be the y value at that point. So if I think about what a graph of sine of x looks like, sine of x starts at the midpoint, and returns to our midpoint. Now the period of sine of x is 2 pi, which means that it completes this full cycle at 2 pi, which is going to make this point in the middle pi. And that means that 3 pi over 2 is right here. So we're going to cut ourselves off right there and ignore the end of the graph, or at least the end of one cycle of the graph. Now, the next thing we're told in the problem is that we should make 6 subintervals. So these numbers are going to be messy, but I will try my best to not make mistakes with fractions. So in order to figure out how this is going to break up into 6 sections, it's not too bad to visualize, but we need to know the actual x values, because the way that we're going to find the heights of the rectangles is by plugging the x values into our sine of x function. So to figure out what those x values are, the first thing I'm going to do is to figure out how wide each of our intervals are, or how wide each of our rectangles are. So Dr. Diddell was calling that delta x, and we're going to find that. Sometimes this is written as b minus a over n. What that means is the endpoint, the starting point, and then the number of rectangles. So here, our endpoint is 3 pi over 2. We were starting at 0, and we have 6 rectangles. So that means that the width of each of my partitions is going to be 3 pi over 2, and then dividing by 6 is the same as multiplying by 1/6. So I would have 3 pi over 12, or we can reduce that and call that pi over 4. So that means that when we come back to our picture, we're dividing this up into increments of pi over 4. So that first x value is pi over 4. And by the time I get to the second value, the second x value, I've done 2 of those pi over 4s. And then that third value is 3 of the pi over 4s. And this is This means that if I were just counting, this next part would be 4 pi over 4, which is the same thing as pi. And if I keep going, that would be 5 pi over 4. And then just to check ourselves, if I go 1 more pi over 4, I'd be at 6 pi over 4, which matches because 6 pi over 4 reduces to be 3 pi over 2. So now I have each of our x values that we would be plugging in. So just to give myself a little bit more space, I will erase that. And now to set up this area, and I'm just making sure I'm all caught up in the questions, and it looks like we're okay. So I'm guessing somebody couldn't read my handwriting. Sorry about that. I'll try to write more neatly. So here's our function, and for this area, we were asked to use right-hand endpoints, which means, and sometimes we talk about those as being the sampling numbers. So our sampling numbers are going to be from the right-hand endpoint. When they say sampling numbers, that just means those are the x values we're using to come up with the y values for the height. So the first x value I would be plugging in is pi over 4. The second x value I would be plugging in is 2 pi over 4, and then 3 pi over 4, pi, 5 pi over 4, and 3 pi over 2. For each of these, the width of that rectangle is the same and the width of my rectangle for each of those is the delta x, or the pi over 4. So when I go to write our area, and I will be careful, just like Didel was in class today, this area is approximately the sum of these rectangles. So I would have pi over 4 for the width. And then to find each of the heights, I'm finding the height by evaluating and finding the y value on the graph at each of these. So at pi over 4, the height here at pi over 4 would be sine of pi over 4. And just so you all know, if no one has prepared you, Dr. Didel definitely includes a lot of trig in his problems. A lot of trig both in the problems that are going to be assigned to you, and then also for your quiz and midterms, you should expect to see trig problems. So he has a high expectation that you have your trig values memorized for our nice angles. So pi over 4 is considered a nice angle. We should know that sine of pi over 4 is 1 over root 2 or square root of 2 over 2. Either of those are fine, full credit either way. I'm a 1 over root 2 person myself. So, so that first height is going to be sine of pi over 4 or 1 over square root of 2. That second height is going to come from using our second x value. So 2 pi over 4 is the same as pi over 2. And sine of pi over 2 is 1. And we can actually see that right here on the graph because we are at that place that's right at the top of our sine curve. Now I'm at sine of 3 pi over 4. So 3 pi over 4, if you're a unit circle person, 3 pi over 4 has put us into the second quadrant. Sine is still positive there, but I'm going to have the same value. So now we've done this rectangle, this one, and this one. This fourth rectangle, because we're evaluating at the right-hand endpoint, sine of pi is 0, which means the height of that fourth rectangle is 0. Now for the height of my fifth rectangle, we're evaluating sine at 5 pi over 4. Well, 5 pi over 4 has now put us into the third quadrant, and sine is negative in the third quadrant, which means I'm going to end up with negative 1 over square root of 2. And then finally, for our last rectangle, to get the height, I'd be looking for sine of 3 pi over 2. And sine of 3 pi over 2 is negative 1. So that height here would be negative 1. So these are all of our heights. So that's for the right-hand endpoints. And looking at the question in the textbook, part B asked us to repeat with midpoints. And the truth is that repeating with midpoints isn't any more difficult. It's just messier. So when the problem asks you to find a Riemann sum and to use the midpoints, what that's going to look like on the graph is that you're actually going to find the x value in the middle of each of these windows. Now, I will say for this particular problem, I don't think that's a reasonable quiz or midterm problem normally for Dedel, because if you think about what the middle of this window is, that would be x equals pi over 8. That's not a nice angle that we're supposed to have trig functions memorized at. So the only way that you can do part B of this problem really is by putting numbers into a calculator.